So in this lesson here, we want to look at how to analyze the equation of a function using derivatives to determine features and then be able to make an accurate sketch of that graph. Okay? So there's a couple of guidelines here we want to follow, and that is when you are analyzing the graph of the function, one of the first things that you would want to do is go ahead and identify the domain and range of the function. Okay, now that's stuff that you learned how to do back in Algebra 2 and pre-calculus and so on. Alright, so that part, though, we want to recognize first. The second thing is determine your intercepts, asymptotes, and also is there any symmetry that we can recognize here? Okay? Because that will help us as we're sketching things as well. Then number 3, this is the part that we really are going to focus in on, and that is locating the x values for which the derivative and second derivative are either 0 or do not exist. In other words, we're finding critical numbers and also potential points of inflection. And then we're going to use those results to find relative extrema, points of inflection. Also, along the way, we can identify intervals where we're increasing or decreasing, and intervals where we're concave up or concave down. Okay? So, we have a little bit of a template here that we could use. And let's actually go in the order that the guidelines give us. So, first of all, our domain and range, okay? The domain and range. What would the domain of this equation here for f of x be?
X cannot be 2 or negative 2.
Good. X cannot be 2 or negative 2. So I'm going to list that in my domain here. X does not equal plus or minus 2. Now that means I either have holes there or asymptotes. As you look at the numerator, what are those actually going to be? The top.
Oh. Asymptotes.
Okay, why?
Because you can't really cancel anything out.
Okay, yeah, if I factored the numerator and denominator, x plus 3, x minus 3, over, x plus 2, x minus 2, I'm not going to be able to cancel out any of those, so I don't have holes. I simply have asymptotes. So I can actually fill this in too. The vertical asymptotes are x equals 2 and x equals negative 2. Alright, so I'm going to actually start sketching as I go, because that'll be kind of help me get a sense for what's happening as I'm going along. So here's x equals 2, there's an asymptote, and here's x equals negative 2, another asymptote. Okay? The next thing that kind of goes together is the range and our horizontal asymptotes. Okay? When you're thinking range, think, obviously there might be a max point or something like that. We won't know that quite yet, but do we have any horizontal asymptotes here?
Yes.
Where?
2. Y equals 2.
Okay, yeah, y equals 2. And we know it's y equals 2 because, why? Yeah, up here we have the same degree. This is what we were just talking about. Okay, so if we distributed that 2 in on the numerator, we'd have a 2x squared on the top and an x squared on the bottom. So our horizontal asymptote is going to be y equals 2 over 1, or just 2. Okay, so I'm going to go ahead and sketch that in here too.
Y equals that.
Okay, whoa.
What happens when you have 0 in the denominator and 0 straight up?
0 in the denominator and numerator?
Yeah.
Well, remember, that's when we have a hole.
Isn't hole just in the numerator?
No.
Oh, just in the numerator.
So,
it's
yeah, on the bottom if it were x plus 3 also.
But it crosses the x.
Okay.
Mr. Nixon, it is all pre-calculus.
It's what?
I said we have learned this in pre-calculus.
We did learn this part in pre-calculus. That's a nice thing. We are now synthesizing things, or we're putting together things that we learned in pre-calculus with things that we've learned here in the last couple weeks, and now we're able to come up with a really, really accurate idea of what this would look like. Okay? Now, a couple other things we can do before we even start looking at our calculus is look at our x-intercepts and y-intercepts. All right, so what are our x-intercepts going to be?
When y equals 0, so you set the whole thing equals 0.
Okay, so what would that be?
Negative and positive 3.
Yeah, it's where the numerator is 0, so that's going to be at x equals plus or minus 3. All right, so 3, 0, and negative 3, 0. So I'm going to put those points on the graph here as well. So 3, 0, negative 3, 0. Okay. There are x-intercepts. How about the y-intercept?
It's 0, 0.
Yeah, it's when x equals 0. So what do we get?
18.
Negative 18.
Oh wait, I forgot to do the denominator. Over
2 times negative 2, so negative 4. So it'll be negative.
Negative 18 over negative 4.
Negative 4.
4.5, just 4.5, not negative 4.
sorry, 9.
Good catch there, Chloe. It's 4.5 because you have a negative over negative. Okay. So here we have 1, 2, 3, 4, 5. So it's going to be at 4.5. All right, so we're already kind of getting an idea of what this should look like, right?
Right.
It looks like we're going to have kind of a parabola-looking thing in the middle. It's not a parabola because it does only approach those asymptotes. But then on the outsides, we're going to have these little curved parts that approach the horizontal asymptote as it goes to the outside, and then goes down to negative infinity as we approach the vertical asymptotes. Okay? So we already can kind of tell what's going on here just from that. You might say, well, what's the point in going on and doing the calculus? Well, we're going to get an even more accurate view of what exactly is going on and also be able to tell some things about the function that aren't necessarily visible but do occur here in the function. All right, so now it's time to do some calculus. All right?
Thought we were going to get out of it.
Yeah.
Oh, so that is what we learned in the past classes.
Mm-hmm.
Oh.
Yeah. So now let's apply the first derivative. The first derivative, we're going to have to use what here?
Quotient rule.
Quotient rule here. So let's go ahead and do that. F prime. You guys can try this on your own I'll just work through it quietly and you can kind of work it through on your own. Okay? So there's our first derivative. 20x over x squared minus 4 quantity squared. Now, what do we get from our first derivative?
Rate of change.
Slope of the tangent line.
Or rate of
What features of a graph are we getting?
Critical values when it equals 0.
Critical numbers when it equals 0, or is
Increasing.
critical numbers, come on guys, critical numbers are when it equals 0 or is undefined, okay? This is the stuff we got to know at this point, guys, really well. All right? So our critical numbers here, what's going to make it equal 0? 0. What's going to make it undefined? Positive or negative 2, okay? So, at this point, there is a table down here, okay? You may not really like using the table like that. You may prefer to just use a sign diagram and put in a negative 2, a 0, and a 2, okay? And then look at the signs of the derivative in each of those intervals, okay? So f prime, what does f prime equal if we go to like negative 3?
It's positive. No,
The-
it's negative.
The denominator is squared, right? So no matter what we plug in, the denominator is going to be positive. So really we only have to care about the numerator. So if I plug in negative 3, I get negative, which means my function is decreasing. All right? And then between negative 2 and 0, same thing. It's still decreasing. Okay? And then from 0 to 2, it's positive, which means our function is increasing. And after we pass 2, same thing, positive, and it's going to be increasing. Now, as you look at what we surmised the graph would look like, you can actually see this. Notice we are decreasing as we go from negative infinity up to 2. At 2, it's undefined. But then here, once we get past 2, until we get down to here, it's decreasing again. Okay? So we are decreasing from negative infinity to 2, or also from 2 to 0. Do not just put negative infinity to 0 because it's not defined at negative 2. Okay?
Can you put it's decreasing in negative infinity to 0 with the exception of negative 2?
I'm confused how you got 2 comma 0.
Hang on. Technically that would be okay, but don't do that. Yeah.
I'm confused how you got 2 comma 0.
Well, if you look at our graph here, once you get past x equals 2, from 2 until we get to 0, it's decreasing
Would that be
again.
negative 2?
Negative, yes, I'm sorry, thank you.
Yeah.
Sorry, negative, yes. Increasing is going to be from 0 to 2.
And then 2 to infinity.
Can we just like write it negative infinity to 0? Or do that?
No, you have to keep it separate there because it's not defined at negative 2.
Okay.
So here we're increasing once we get past 0 until we get to 2, we're increasing. At 2 it's undefined, but then once we get past 2 to positive infinity, we are increasing again. Okay? So, question here, what extrema do we have? We have a minimum at where?
Yeah.
X equals 0.
At x equals 0, because right here, notice here, there's a min, And that's going to be the point 0, we already found that, 0, 4.5. That y-intercept was the minimum point. Okay? Does that make sense, everybody?
Yeah.
Okay. Now, our last thing here is finding possible points of inflection and determining concavity as well. Okay? Now, second derivative. We're again going to need to use the quotient rule, which you guys know how to do, so I'll let you do that real quick as I do it. Okay. Okay? So we should be able to get to negative 60x squared minus 80 all over x squared minus 4 cubed. This is where simplifying that quotient rule, because we used the chain rule, so I factored out an x squared minus 4 on the numerator, and I was able to cancel with the denominator. Okay? So now I have my second derivative. What are the potential points of inflection going to be? Or where are the potential points of inflection going to be?
So when it's equal to 0, when these are different, so there will be negative and positive.
Negative 2.
Okay. Well, let's look at that numerator a little more closely here. If I take out a negative, say 20, that's going to give me a 3x squared plus 4, right? So what's going to make my numerator 0?
Square root of minus 4 over 3.
All right, and is the square root of minus 4 over 3 a real number?
No, it's not.
Nope. So there's nothing here. There's no real number that's going to make this equal 0. So what else do we look at for possible points of inflection? Denominator equals 0, okay? Well, that's where x is plus or minus 2. However, we already know that at positive and negative 2, what do we have?
Nothing. Leave it as for
We have asymptotes, right? So can we have a point of inflection where we have an asymptote? No. All right? No. So since those are asymptotes, we have no points of inflection. Now, does that mean we can't change concavity?
No.
That's a good question. Let's try it out. are those still numbers that we need to consider? Even though they're not going to give us actual points of inflection, will they still impact our graph? Yes. All right. So we need to check here. We need to check the second derivative, and you can either use the table down here, or we can simply do it with a sign diagram like we did before, but this time with the second derivative. And I'm going to put -2 and +2 here. And if I plug in like a -3 into my second derivative, notice here, -3 squared is going to be positive. -3 squared is a +9, minus 4 is a positive. So if I have -20 times a positive over a positive, what do I get? A negative number, which means I'm concave down. Okay? Concave down. So that's over the interval from -infinity to -2. Okay? That's concave down. Now I test in between. If I plug a 0 in, what am I going to get? Positive or negative?
Negative.
Negative again.
Well, I'm hearing both.
Wait, no.
No,
Positive,
it's
positive.
positive. It's positive. It's gonna be a negative over a negative.
Yeah, I'm going to have -20 times +4 over a negative cubed, which is negative. Negative over negative is positive. So here I am concave up. Okay? So we are concave up over the interval from -2 to 2.
And then it's gonna be concave.
And then if you plug in a +3, it's going to give you the same thing as when you plugged in a -3, because those were squared. So that's going to be minus, so we're going to be concave down again. So we're concave down over -infinity and -2, or from 2 to +infinity. Okay? Now, I don't know which you guys prefer, if you like making those tables, or if you just like using the sign diagrams. It's totally up to you. The key is that you're able to get to what we're looking for, okay? So in this case, we have the interval concave down over here. We have concave up here, okay? We have intervals of decreasing and increasing. So this might make it a little harder to see, but yes.
I'm having trouble understanding why the second derivative gives you the concavity. I know it gives you because you already learned it.
Well, concavity, like by definition, is the rate of change of the rate of change.
Why is
It's showing the rate of change of the rate of change, which is our second derivative.
why is the rate of change of the rate of change of concavity? I know it's a
I mean, that-
shape. Why is the shape?
Oh, well, it's because, like in this case here, when you're concave down, all the tangent lines are above, they're on top of the function. So it's concave down because you'll notice here the slopes of those tangent lines is decreasing. Okay?
One way I remember it too is concave up, the U in up is concave up, and the N in concave down is concave down.
That's a great way of remembering it too.
Down.
Okay?
This part I already knew from study a long time ago.
Okay. Yeah, and here, you can see not only are the tangent lines below the function here, but also if you go left to right, the slopes of those tangent lines start negative and they're increasing until they get to 0, and then finally they're positive. All right, so the slopes are increasing.
The rate of change.
Excuse me.
Thank you.
Okay.
All right. So whether you use the table down below or number lines like I prefer using, it's totally up to you. The thing with the table is you just have to set it up, know how to set it up properly. But you can see our graph, our sketch here looks exactly like what we have here. Okay?
Convenient.
Yeah.
Oh, mine does not look like that. Never mind.
Well, it should look at least kind of close. So.
Yeah, I'm just not good at it.
Okay, so let's look at example 2 here. We have the function x squared minus 2x plus 4 all over x minus 2. And let's start first of all using the same order that we were looking at before, and that is, first of all, trying to identify what the domain and range would be. Okay? And for domain, we're specifically looking for asymptotes or holes. All right, so what is something, or what would our domain be for this function? All right, all real numbers except 2. Okay, so x cannot equal 2. All right, so we see that from the denominator there. X cannot be 2. Okay. Now the range. What are you really gonna kind of think about when you're talking about the range? Because we don't know where max or min points are, but what can we tell just by looking at this function? What did we look at yesterday? Yes, okay, yeah, horizontal asymptotes. Do we have any horizontal asymptotes here?
Yes. No.
Yes, no?
That was bigger on
top.
none.
Bigger on top, none. So there are no horizontal asymptotes, all right? Which means as far as we can tell right now, the range will be all real numbers. Now, there may be a maximum or something that limits our range, so we're not going to put anything right now. But so now we have an idea, and we know there are no horizontal asymptotes. One thing we do look at, though, is that domain, x cannot be 2. That means 2 is either going to make a hole or it's going to make a vertical asymptote. And which is it in this case?
Oh, a hole, because you can cross it out.
Okay, what would we cross it out with?
Minus 2.
Oh, minus 2. Wait a minute.
So you're saying that fact...
No, we can.
No,
We can.
Okay, can we factor that? Top?
No.
No. So there's not going to be anything that we can actually cancel out here. So if it doesn't cancel out, it's a vertical asymptote. Okay, so vertical asymptote is at x equals 2. Now I'm going to take a second. I'm going to actually sketch this as we go. Okay? So vertical asymptote is at x equals 2. There we have it. Okay? Now, there is one other element on this particular one that can happen when there are no horizontal asymptotes. Okay? And that is, notice how the degree in the numerator is bigger, but it's only 1 degree bigger. Do you remember what we got when that was the case? What did we get when the degree was exactly 1 degree higher than the numerator? How about one of these? A slant asymptote. Okay? A slant asymptote. So let's take an aside here and look at this real quickly. It was x squared minus 2x plus 4 over x minus 2. remember when the degree is exactly 1 lower, we can actually divide, okay? And remember, we divide and then ignore the remainder. Okay, so I'm going to actually use synthetic division here because that's cool and easy. Okay, so I'm putting these here. I bring down the 1 times 2, that's 0, times 2, 0, that's 4. Okay? So the 1 is now the x, the 0 is the constant, and the 4 is over the x minus 2 again. Alright? So to determine our slant asymptote, we ignore the remainder, and it's just y equals x plus 0, or y equals x. Okay? So that's one thing it's easy to forget about. Now, if you do everything else right, you'll still get a pretty accurate drawing, but there may be an element of it that's not totally accurate. So just look out for that when you don't have horizontal asymptotes. Okay? So this is a slant asymptote. Okay? So let's get back to this. We have this line y equals x now. That is the slant asymptote to work with. Okay? So that's all the first part. Domain and range, and then we also got off on the slant asymptote. So now we're looking for intercepts. Alright? Intercepts. So what are our x-intercepts?
We have to use the quadratic formula.
Okay, the numerator does not factor, so we'd have to use quadratic formula. And you should always do the discriminant of that first, right? The b squared minus 4ac. Why should you always do that first? Make sure there is a solution, okay? So the quadratic formula, you got the plus or minus the square root of b squared minus 4ac. So I'm going to, for this numerator,
Can't we just like use quadratic formula?
yes. But remember the part of the quadratic formula in the radical, that's going to determine if you actually have two real solutions if it's positive, you'll have one real solution if it's 0, and you'll have imaginary or complex solutions when it's negative. So that's why rather than do the whole formula, let's do that b squared minus 4ac first and see if we actually get an answer. All right? So it's not right or wrong. This is just, it can save you some work sometimes.
Wait, so 0 equals 1 solution?
Yes.
What is positive?
Two real solutions, because you're taking the square root of a positive number.
Oh, right.
All right?
What if there's no solution if you do that?
Well, then what does that mean about our x-intercepts?
There are none.
There are none. Okay? It's possible for a graph not to hit the x-axis. All right? So we do this and we get b squared, so that's 4 minus 4 times 1 times 2. Or sorry, not 2, 4. And that's negative, right?
Yeah.
So what does that mean? There are no x-intercepts. There are none. Okay?
Wait, so how do you do this like asymptote again? You just take the remainder of the.
We ignore the remainder, you just divide. See, we just divided and I ignored the remainder.
Oh, okay.
Okay? Alright, so y-intercept. What's our y-intercept here?
None.
Now there is one. 4 over negative 2, which is negative 2. Okay? Remember, y-intercept, you plug in a 0 for x. So we'd have 4 over negative 2, which is negative 2. So I'm going to put that on the graph here. Okay? Now, just from what we are familiar with already, we know that this is going to look something like this. There's going to be approaching this asymptote, going to go through this and approach the slant asymptote, okay? And then there's going to be this other piece up here that kind of does the same thing. So that's what we have an idea of as far as what this is going to look like, okay? Now,
How did you know that it was up? Like, could it just be down there? Or does it have to be?
Well, in certain cases it's possible, but there's nothing yet to indicate that we would. Usually these hyperbola-looking things, these rational functions, the parts are like on opposite corners from each other. So just from experience, this is kind of what we think it'll look like. All right? But while that would have been good enough for pre-calculus, we can do better than that now. So let's look at how we would do better using our derivative. Should have done. There we go. So let's think about our first derivative. Okay? So we're going to get our first derivative. All right. Sorry we lost the audio on that. Okay? But you'll at least, it records the view, but for some reason when my battery dies, it loses the audio. I don't know why. Anyways, we'll have it from here on out. So the second derivative, let's put that back. The second derivative, f double prime of x times x minus 2 squared minus x squared minus 4x times 2 times x minus 2 to the first power. That's all over x minus 2 squared squared, which is the fourth power. Okay? Now, we use the chain rule within the quotient rule. So you remember what happens here. Every time that happens, we're able to pull out a common factor in the numerator. Okay? That happens every time. So that's one of those things you should be picking up on here. Oop, let's get back to a pen. So we have x minus 2, and then in parentheses we're going to have 2x minus 4 times x minus 2 minus 2 times x squared minus 4x. And again, this is all over x minus 2 to the fourth. Okay, so that's one nice thing here. This is going to cancel with one of these and leave only 3 in the denominator. Alright, and then finally here we have 2x squared minus a 2x squared is 0. We have negative 4x minus 4x, negative 8x, plus 8x, that's 0. And then we add, we have a plus 8 over x minus 2 cubed. Alright, so the only potential point of inflection is when x equals 2. Okay? However, 0 won't make that 0 or undefined. Okay? That's the only possible one. However, we know there's already an asymptote there. So what does that mean? There are no points of inflection here. Okay? There are no points of inflection because the only number that we get from our second derivative is already an asymptote. Alright? So from looking at what we've got, we can though see concavity. To the left of negative 2, we're concave down. To the right of negative 2, we're concave up. Alright? And that's it. Okay? So, there's our second example There's a lot to these. They take a while. You just gotta be patient and careful. Alright, sorry we lost the audio on that. Okay, but you'll at least, it records the view, but for some reason when my battery dies, it loses the audio. I don't know why. Anyways, we'll have it from here on out. So the second derivative, let's put that back. The second derivative, f double prime of x times x minus 2 squared minus x squared minus 4x times 2 times x minus 2 to the first power. That's all over x minus 2 squared squared, which is the fourth power. Okay? Now, we use the chain rule within the quotient rule. So you remember what happens here. Every time that happens, we're able to pull out a common factor in the numerator. Okay? That happens every time. So that's one of those things you should be picking up on here. Oop, let's get back to a pen. So we have x minus 2, and then in parentheses we're going to have 2x minus 4 times x minus 2 minus 2 times x squared minus 4x. And again, this is all over x minus 2 to the fourth. Okay, so that's one nice thing here. This is going to cancel with one of these and leave only 3 in the denominator. Alright, and then finally here we have 2x squared minus a 2x squared is 0. We have negative 4x minus 4x, negative 8x, plus 8x, that's 0. And then we add, we have a plus 8 over x minus 2 cubed. Alright, so the only potential point of inflection is when x equals 2. Okay? However, 0 won't make that 0 or undefined. Okay? That's the only possible one. However, we know there's already an asymptote there. So what does that mean? There are no points of inflection here. Okay? There are no points of inflection because the only number that we get from our second derivative is already an asymptote. Alright? So from looking at what we've got, we can though see concavity. To the left of negative 2, we're concave down. To the right of negative 2, we're concave up. Alright? And that's it. Okay? So, there's our second example. It's a lot to these. They take a while. You just got to be patient and careful.